Okay, great. Okay, so let's recap what we did in the last class. We introduced the Dirac equation, which is this, and I told you that this Dirac equation has a solution, which is, so this equation is in terms of some field psi, which has 4 components. So this is called a spinor, and why it's called a spinor I will tell you briefly. And this is 4 components, and this gamma mu is any matrix 4 cross 4 matrix which satisfies this equation. And one particular example that we usually work with is this form of gamma mu's, where this is gamma naught and these are gamma I, where sigma I are the Pauli matrices. And then we look for solutions of Dirac equation, and you can have, and I showed that each of the components psi 1, psi 2, psi 3, psi 4, each of them individually satisfy the Klein-Gordon equation, plus or minus depending on the choice of signature, m square psi. And then, so this equation has solutions like e to the power I plus minus p dot x. So the answers we considered was u of p e to the power I p dot x, where u of p is a spinor. It has 4 indices. So this is the 4 index of it. हेलो, नमस्कार. अच्छा, ये तो नॉर्थ कैंपस में है, C37S2. हाँ, आप स्पीड पोस्ट लाए हैं? एक सेकंड. हेलो, हेलो. हाँ 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 हाँ. नॉर्थ से लेना है, पोस्ट लेना है कुछ. किसने बुलाया आपको? हाँ, अच्छा अच्छा, मेरे लिए पोस्ट है, साउथ कैंपस के पोस्ट ऑफिस में छोड़ा है. ठीक है, मेरे ऑफिस में भेज दीजिए. A7 ऑफिस है, A7. फिजिक्स ऑफिस में दे दीजिए. हाँ, अनुग्रह सर के पास दे दीजिए. सॉरी अबाउट दैट. Also recorded for posterity. Okay. So solution to this equation is given by up to the power minus ip dot x, and then I showed that if I plug this answers in the Dirac equation, I will get a form of up which is like this, where remember sigma is identity, is a 4 component object with identity and sigma meaning the Pauli matrices sigma 1, 2, 3, and similarly minus sigma. And this xi, it can be any arbitrary 2 component object. Okay, so this is a 2 component object which is arbitrary. So up to this, so the solution of Dirac equation is this, which has, where you can fix this xi. I mean, you can put any value of the xi and it will still satisfy the Dirac equation. So there is a, so these 2 xi's are the same, but you get to choose any xi. So any xi will give me, this whole thing will give me a solution of the Dirac equation. And so if I consider a xi, most general form of xi would be some linear combination, so it will be like some AB, where these are arbitrary complex numbers, and you can real numbers, and you can write it like A0 plus B0 1. Okay, and so this is where spin comes from, and this is why electrons have spin. So you can see, just like a spin system, this is a two component object. So spin systems are described by two component objects, right? And we know that for example, if I am considering spin plus minus z in the plus minus z direction, those spin state vectors are given by the eigenstates of the sigma 3 Pauli matrix. You know this, right? So the eigenstates of the sigma 3 Pauli matrix are, so this is the spin in z direction, and if I am talking about plus minus, these have eigenvalue plus minus 1 under the Sz matrix, or the sigma z or sigma 3 matrix. And so this will be some two component object, 1 0 0 1, something like that. And so a general spin system is described by a two component object. And we know, of course, that electrons have spin. And where does that spin come from? Now we can see from Dirac equation that the solutions themselves, or the Dirac equation themselves, have spin, in the sense that they are described by a two component object. If we specify some two component object, that gives a solution of the Dirac equation. So spin is inbuilt in the Dirac equation. So this is one solution with minus ip dot x. Similarly, you can take ip dot x, and that will give you another solution, and that will look like this, where eta is again some two component object. So the simplest solution is when the 3 momentum is 0, and then P naught is just m, and then you get the solution, which is square root of m for Vp eta minus eta, and for Up square root of m. So this is a system at rest, and it only has spin, so it is completely described by its spin. Once you specify what xi is, it specifies the classical solution. And once we consider these solutions to be quantized, once we go to the quantum theory, this corresponds to the spin of the particle. Okay, so let us write the most general solution classically now. So again, we have this e to the power ip dot x and e to the minus ip dot x. These are the solutions, and we just saw that there is a these are given by these xi's, which can so these are given by this xi's, which themselves have a basis of 2 dimensions. So these are 2-dimensional vectors. So a xi, most general xi, can be written as a sum of 2 of them corresponding to spin. So it could be plus half or minus half. So we give here a spin index corresponding to that. So spin, and there's a sum over S, which is plus minus 1. This corresponds to this freedom. When I am specifying u, I can choose sigma out of a as a any linear combination of these vectors. And then, of course, I have integral over all possible momenta, just like before. Square root of t pp, everything as before. Remove this a little bit. And finally, I can multiply some arbitrary coefficient to these quantities. So by convention, I write something like dsp. And so here I am working in the Schrodinger picture, not quantum mechanics yet, but yeah, and this we call C star sp. Okay, and these b and c will become operators, creation annihilation operators, when we go to the quantum theory. Okay, so this was the recap of the last class. Now we will pause for questions. Any questions from this? Okay, so now I'm going to tell you a little bit about spinors and what they mean actually, what is the geometric meaning of spinors. This is not needed for exams, and this is just for your knowledge, so you understand why. I mean, at this point it might seem a little out of the blue why we wrote a 4-component object and why we are saying that an electron is described by a 4-component object. What does this, where did this, of course when Dirac wrote it, he just wrote it, he just was trying to write an equation which is both relativistic and quantum, and he simply came up with the equation. But now we know a little bit more that why it is relativistic and what kind of object these spinors are. So I will tell you a little bit about symmetries of space-time and spinors. Again, this is more for you to have an idea that why spinors show up in physics. Okay. So I want to talk about here symmetries of space-time. So what kind of symmetries our space-time has, meaning what kind of operations that we can do which will leave our observations invariant. So one thing we can do is translation both in space and time, meaning that if we translate everything by some distance, and if our space and time are homogeneous and isotropic and all that, then nothing will change. Of course, here we are assuming that we are working in the Minkowski space, which is homogeneous, isotropic and all of that. And more mathematically, you can say that what are the operations that keep this element of distance unchanged. So what I can do to x, which will keep ds square fixed. Those are the symmetries. And one is translation, because if you do a translation, then dx prime mu is the same as dx mu, because this is a constant. So this does not change. And Lorentz transformations, of course we know from special relativity, Lorentz transformations are symmetries. If I go from one frame to another, nothing changes. So they too also keep this unchanged. And Lorentz transformations can be, of course, classified into rotations and Lorentz boosts. Okay, so totally we have how many symmetries? So we have here 4 translations corresponding to 4 dimensions. We have how many rotations? 3 independent rotations corresponding to 3 axes. And how many Lorentz boosts? Again 3, because we have either you can have Tx, Ty or Tz. So we can have boosts along x, y and z directions. Okay. And corresponding to these space-time coordinate transfer, space-time symmetries or space-time transformations, we can classify various physical quantities into things like scalars, vectors and so on. So quantities which are independent of coordinates have a specific transformation property when I make a coordinate transformation. So coordinate independent objects, which means physical objects, i.e. physical quantities, have some specific rules when I go from one coordinate system to another, which says that the physical system is unchanged. So the way we express them in terms of coordinates must be related to each other. And so scalars, what is the rule for scalars? Let's say a scalar called m, when I make a change of coordinates, it doesn't change. That's a scalar. It's still m. And if I have a vector, its coordinates under Lorentz transformation will change in the exact same way as the coordinates change. So this is a vector. Okay. And today we'll learn about a third thing, which is spinors, which is neither scalars nor vectors nor tensors. So tensors, of course, also we know. Something like G mu nu, which will change as lambda mu alpha beta, G alpha beta. And spinors is a different kind of thing. But before talking about spinors, we also need to talk about fields, because we are talking about here fields. So a scalar field, how does a scalar field change? So take a scalar field and consider the simplest example of a coordinate transformation, a translation. So what I am doing is I am taking this coordinate system, which is x, and this is phi x, and I am translating it by some distance a. So this is the next picture where the coordinate system has been translated by x, by a. Okay, so this this distance over here is a. And the new field phi prime x, of course the value at a given physical point remains unchanged. The only thing that has changed is that I have shifted the coordinate system. I have translated the origin. I have defined a new coordinate system which is a distance away. So for a scalar, because this is a scalar, the field at this point and the field at this point are the same. The only thing is changed is that I am in this new coordinate system, and so I should have the field in this coordinate phi prime x. So phi prime x should be phi of x minus a, because you can see here that in this coordinate system this is some x minus a. So this is how I have a change which is only axial for the field. Generally, if I have a transformation x goes to some lambda x, which is a matrix multiplication, by this I mean lambda mu nu x nu, not writing fully, just writing in terms of a matrix multiplication, then phi prime x is phi of lambda inverse x. Just like here, the transformation was x plus a, what appears here is x minus a, the inverse, because once the coordinate system shifts, the point shifts in the other way. So similarly, it's this. For a vector field, it's very similar, a prime mu x. So this x, inside there will be a lambda inverse, and outside there is a lambda mu. Again, this is all just for knowledge and not exams or anything, so you can be not worried. Similar, very similar. Beta, and inside it's this. So x always goes to lambda inverse x, and if I have the coordinates, the components here, they will change like a scalar vector or tensor. Now a general rule of how things should change is when x goes to lambda x, the field psi should change to, this part is of course the function will be of lambda inverse x, and psi should change by the action of a matrix which I am calling d of lambda, meaning some function of lambda acting on this. Okay, so what I am saying is, suppose I have a general field. I am not telling you it's scalar, vector, tensor or anything, and I am saying that it has some components A. So what is the most general possible way it can transform? So what I am saying is x goes to lambda x. This could be a rotation. Let's say x goes to lambda x is some rotation, and then psi goes, I am saying that the change in psi should of course depend on how much I have changed the space-time, how much rotation I have given. So it should be a function which I am calling d of lambda acting on psi. It should be some function. I have not specified yet. For vectors, d of lambda is just lambda itself, right? But what is the property that d of lambda has to satisfy? Suppose I take two rotations. Rotation 1, which I call lambda 1, and then rotation 2, lambda 2. And this object psi, which is some kind of field, will change by, first it will change by d of lambda 1 psi, and the second rotation it will change by d of lambda 2 psi. But if these are two rotations, for example, this lambda 1, lambda 2 multiplied will give another rotation, which I can call lambda 1, lambda 2. So I could either give this in steps or I could give it directly. So if I gave it directly, psi would change by d of lambda 1, lambda 2 psi. So for consistency, it must be that d of lambda 1, lambda 2 psi is equal to, if I give it in steps. So d of lambda 1, lambda 2 should be equal to d of lambda 1, lambda 2. Okay?
So is
Yes.
that psi prime, like we are taking lambda inverse x there?
This one?
In the second equation, like psi is written as this one. The left hand side should be psi.
No. So this whole thing is equal to psi prime.
Yeah.
This is equal to psi prime. So here I have drawn an arrow. Means psi changes to this, and this whole thing is, you're right. This whole thing is equal to psi prime a. Okay. So this is psi prime a. So all we are saying that if there is some physical field psi, if I make a space-time transformation, and if I demand it changes, so it should change by some function of the space-time transformation, and it should satisfy this property at least for consistency, that if I take two rotations or two transformations in series, or if I take it at one go, they should give the same result. They should change psi by the same amount. That's it. And so, for example, we have for scalars, what is d psi for scalars, d lambda for scalars? It is simply identity because it doesn't change. And for vectors, d lambda is the lambda because that is how it changes. Now we will see what is it for spinors. It will be something different. Before I can talk about that, I have to talk a little bit about generators of transformations. Have you encountered generators of transformations before? Okay. So very briefly, for to give an example of rotations. So if I have this, let's say R is a rotation matrix. This is a rotation. Then we know that rotations keep this distance invariant. If I rotate, the distance between 2 points doesn't change. And from there you can derive this relation which says that R transpose R is identity, where R is the rotation matrix. Now if I consider an infinitesimal rotation, where it is just very small rotation, so it is R is identity plus some small matrix omega, then you can show that substituting this here, you will find that this omega has to be a antisymmetric matrix. Okay. So an infinitesimal rotation, so I consider an infinitesimal rotation, and I find that that has to satisfy the property of being antisymmetric. So an infinitesimal rotation is antisymmetric. And this is what we call, these all possible values of omega are what we call the generators of rotation. So I can write down what is the basis of, this is 3 cross 3 because rotation 3 dimensions. So what is the basis of 3 cross 3 antisymmetric matrices? and these matrices are called the generators of rotation. So we have 0, minus 1, 0, 0, 0, sorry, 0, 0, 0, 0. We have 0, 0, minus 1, 0, 0. I think this is correct. And one more, 0, 0, 0, 0, 0, minus 1, 0, 0. Okay. So we have 3 of these guys, and these are the antisymmetric matrices which correspond to infinitesimal rotations. So I can write any rotation or any infinitesimal rotation as a linear combination of these matrices. Why? Because the most general infinitesimal rotation is simply an antisymmetric matrix. So any antisymmetric matrix can be written in this basis of antisymmetric matrices. And these are called generators of rotation, meaning these are the independent rotations, infinitesimal rotations that I can give. And they correspond to the rotations along the 3 axes. Right? If you remember your quantum mechanics, they correspond to your Lx, Ly and Lz angular momentum operators, which are generators of rotation. And so what we have to do now, if I want to rotate, I have to specify how much I want to rotate by. So I have to give some number. So a general rotation will be, so if I call these matrices, let's say JAB, so a general rotation, finite rotation, has the form e to the power sigma AB JAB, where sigma AB, JAB are these 3 matrices. So here we have 1, 2, 3, so we call this, for example, something like J12, J23 and J13. These are the 3 JAB matrices, and lambda AB are numbers, 3 numbers, which are telling me how much I am rotating by. So they will say, let's say if I want 30 degree along z axis, so I will give some specific numbers and I will give a specific rotation. Suppose I say 30 degree along z axis. So then JAB will be the rotation in the 1-2 plane, meaning xy plane. So I am rotating in the xy plane, and I will give this numbers will specify my 30 degree angle. And this whole thing is of course itself a matrix, because if I multiply these JABs, J12 by some number, 3 by number, something, the sum of that is a matrix, and if I exponentiate that, that is also a matrix. So sigma AB, JAB is just 3 numbers, sigma 1, 2 multiplied, so it looks like 0 minus sigma 1, 2 minus sigma 1, 2, 0, 0, 0, 0, 0, plus similarly another number, minus sigma 2, 3, minus sigma 2, 3, raised to 0, plus this whole thing is a matrix, and when I exponentiate this, that is also a matrix, and that gives a finite rotation. Okay, so this is what is called a generator of a transformation, and when you exponentiate the generator, you get a full transformation. Similarly, when we do Lorentz transformations, we have a similar condition, omega mu nu plus omega nu mu is a similar antisymmetric condition, but now these are 4 into 4 matrices because these are in space time. So again you write basis in terms called M01, M, so instead of J we have M, so M12, M23 and so on. So the rest are similar, 0, 0, 0, minus 1, everything else 0 and so on. And the general transformation is given by, let me call it again, MAB, where AB is now running from 0, 1 to 3. Okay, so a vector transforms under the rotation matrix, right? So if I have a vector A prime alpha is lambda alpha beta A beta into this part is whatever it is, same everywhere, and this lambda alpha beta is the Lorentz transformation rotation matrix, which is given by e to the power half lambda AB M AB. Okay, because this is a finite Lorentz transformation. Just like this was a finite rotation. So similarly, if I had a rotation, I would write x prime j is rj I xi, and this rotation matrix would be given by this because this is a finite rotation. Now spinors transform like this by some s lambda, which is a function of the space-time transform lambda, but it is not equal to lambda itself. This is defined by some e to the power I. These are the parameters again, you specify the parameters, but instead of this m matrices, we have a different set of matrices S. So for vectors, this was e to the power I sigma rho sigma m rho sigma. Here it is S, and S is defined as by the gamma matrices in this following way. Okay, so this is the definition of S, and one can check that S satisfies the property that I told you in the beginning, that if I take two transformations, it gives the same thing. And therefore, the point I want to convey here is that spinors are different from vectors, although they are also 4-component objects, despite the fact they transform differently under Lorentz transformations. The way vectors transform is this. This is how the Lorentz transformation of vectors work, and the Lorentz transformation of spinors works in a different way. So this is the only takeaway message of this part of the lecture, that spinors are 4-component objects. They transform under Lorentz transform in a specific way, which is different from vectors. And somehow Dirac didn't know all this background theory at the time when he discovered them, but later people understood that, okay, why does this work? How do they transform? What are these objects? Are they vectors, scalars, or something else? And they realized that they're indeed something else, but they also transform under Lorentz transformation in a specific way. Okay, so when you, in the future, if you learn group theory, you will learn more about how these things are, how these transformations work. Okay, so I will pause here for questions.
So that is a commutator. That's a rho.
Yes, this is a commutator of the gamma matrices. So gamma matrices, we said, we introduced gamma nu mu plus gamma. So those guys. Yes.
And from this we can find S of our omega, S of our lambda.
Yes.
Then, but as S of lambda don't have any index, like they have two contravariant and two covariant. So it is a scalar kind of thing.
No. So again, just like this, I showed you these guys. We summed over. These were matrices. So similarly here, this S's themselves are matrices. So each gamma is a matrix, and S rho lambda is itself a matrix. This is not a number; it's a matrix. These are numbers. So these are telling you which Lorentz transformation you are considering. So this is telling you the 30-degree rotation, or boost by 60, boost by velocity 0.6 c, whatever. That information is here, and these are telling you how spinors will transform under that particular transformation. And each of these are matrices, because S rho lambda is gamma rho, gamma lambda plus gamma lambda, gamma rho. Gammas, remember, are themselves matrices. We wrote down some matrices somewhere. These are your gammas. These are matrices. And when you multiply by some numbers and add, the whole thing is a matrix, just like the example I gave you here. Like this whole thing, although it looks like all the indices are added, because J's themselves are matrices, the whole thing is a sum of matrices, which is a matrix, and then when you take exponentiation of that, that is also a matrix. Okay, so you know how to take exponent of a matrix. Exponent of a matrix is defined through this relation A, the Taylor expansion 1 plus A plus whatever A is, A dot A by 2 factorial, like this. Okay, so that's also a matrix. Okay, any other questions?
How we can use that index like alpha and beta, but they are significant?
Sorry, which? So this whole thing is because this is a matrix, this will have its alpha and beta indices. So this this thing is a matrix, and so this will have its usual matrix alpha beta index.
So again you have to sum over beta because
Yes.
that is the index.
Yes, again you have to sum over beta and you will get something. Okay, so this again, this all this was just for idea. So let us come back to let me see. Let us come back to this. What is in the syllabus? Okay, so now we simply want to quantize the Dirac field, and quantization is simple. We simply take those coefficients that appeared before in this example and we promote them to operators. We know this. So these guys will act like we have these coefficients here and we make them operators. We know they will become some kind of oscillators. Okay, so this is one operator and this is another operator. And by convention we choose this to be dagger and like this. And similarly, you can write psi dagger x is s is equal to 1 to b3b by 2 pi cube. 2b. Now you just take dagger of this. I'm not going into it, and you will get all of that. Of course, you can be more systematic. You should be more systematic and start from the Lagrangian and do all the steps. So the Lagrangian in this case is given by this is the Lagrangian for the Dirac equation, where I'm using this notation psi bar, which is nothing but psi dagger into the gamma 0 matrix. This is a usual notation that is used. This is called a Dirac conjugate. Okay, and then you can derive. So I will not go through the calculations here for fermions, which are messy. I'll just tell you what the results are. The Hamiltonian density, just like in the usual process, and you get this. This is the Hamiltonian density, which you can then transform into, by substituting psi by this value, you can get operators. Again, there was a long calculation for scalars. There's a similar and even longer calculation, which I will spare you, for the Dirac fermions, but the result is something that you might expect. It looks like this. So this is the expression for Hamilton. It's slightly different from, for example, complex fields, because there's a minus sign here, and there's b dagger b minus c dagger. So that is the form that we get. And if you have followed some of the previous classes, you will expect now that these creation annihilation operators should correspond to fermionic oscillators and not simple harmonic oscillators, because we showed in the previous classes that if I consider fermionic oscillators, they satisfy the Pauli exclusion principle. They give me fermions, basically things that behave like fermions. So these oscillators will also be fermionic oscillators, meaning they will satisfy anti-commutation relations and not commutation relations. But you could ask, like, what would go wrong if we said that they satisfy commutation relations? Because earlier that's what we were doing. We were saying that these b daggers should satisfy commutation relations. Basically, for the scalar field, we were imposing the commutation relation on the field and its conjugate when quantizing, and this was giving us the A dagger commutation relations, and that's how we were operating. So if we also impose commutation relation on this field, on psi and its conjugate, then what would go wrong? And I will just tell you what would go wrong. So if we impose commutation relations on this, we get that, again, sparing you the calculations, we'll get that the oscillators satisfy these commutation relations. We're using something strange, which is that the C commutation, C guys have a minus sign. Why is this a problem? This is a problem because suppose now you consider the 0 to be annihilated by all the C operators, and then you will consider a particle to be created by the C daggers, the usual way. But then if you try to take the norm of this state, C dagger, this thing, what do you get? You get C dagger and the conjugate is this. So this again can be written in terms of the commutation relation like this. This part annihilates 0 and you are left with this dagger thing, this commutation. But this commutation has a minus sign. So what you will get is something that has a minus sign. Something 0, whatever here, the thing here is, and a minus sign. So what does this mean? This means negative norm, meaning negative probability, which is nonsensical. So this is nonsensical result. Okay. So then you might think, okay, let me then say that maybe this is not the creation operator, maybe CS is the creation operator. That could save me, because if I say this is 0, then I don't need to worry about states that are created by acting on this. I will define these to be my particle states. So I will switch the definition of saying that instead of calling this the creation operator, I will call this the creation operator, and then I will not have negative norm states because the action of this will give me 0. But that also has problems, because when you take the Hamiltonian of this with the dagger, this has positive energy and the other guy, CSP, this has negative energy. So which means that if these are your states, particle states, then these states will have negative energy. So either you have negative norm, or if you want to avoid that, you run into negative energy. And it's not just negative energy, it's infinite negative energy, because you can keep acting with this and you can keep decreasing the energy of the system until you get minus infinity. So this is obviously a system with unstable ground state, because the ground state has negative infinite energy. If that was so, obviously we would never see any excitation, because everything would go to the lowest energy state, which is negative infinity, and nothing would be ever seen. So this is bad. And the solution is simply to say that instead of commutation relations, the fields will satisfy anti-commutation relations. As we have seen before, that solves everything. So what we do is we impose anti-commutation relation on the fields. This gives us anti-commutation relation on the oscillators. And now note there are no annoying negative signs, both are positive and everything is fine. It's just the fermionic oscillators have the same properties we have already seen, which is Pauli exclusion principle, etc., etc. The last thing very quickly is that here also there is a symmetry, which is psi equals to e to the power I alpha psi, and corresponding to this symmetry, this is the symmetry of the Dirac equation, there is a charge which is defined like this, and in terms of oscillator it looks like this. And then we define our physical charge by this convention where we multiply minus E, which is the charge of the electron, into this operator Q. Why? Because now if I have a B particle, the charge of the B particle is negative E, minus E, and charge of the C particle is plus E. So what is this? Okay, I have a symmetry, corresponding to symmetry I have a conserved charge. I write the charge like this, and this B particles, with this definition of charge, the B particles will have plus 1 charge and the C particles will have minus 1 charge. But because of our usual convention in electromagnetism, we define a new charge operator, electromagnetic charge, by multiplying this Q with a minus E. So that our B particles have a minus E charge and C particles have a plus E charge. So what is the B particle? It's the electron. It's the electron, it has minus E charge, and the C particle is the antiparticle of the electron, which is the positron. So just like we have seen that whenever we quantize a field, we get a particle and an antiparticle whenever there are two different particles. And here also, just like in the case of the complex field, we have a particle-antiparticle pair. And if you do a time reversal again, like in the previous example, on the electron, you will get a positron with opposite momentum and also opposite spin, because spin will also flip when you time reverse. So everything is the same as before. Okay. So with this we complete Dirac equation, we complete fermions, and we have basically completed all of free fields. In the next class we will start with interacting fields. Okay, so I will stop.